Hey y'all, how are you doing today? My name is Thomas Nield. I am very excited to talk to you about... Hold on. There we go. How's that? Okay, great. Awesome. I can speak really loudly too, just as a backup. All right, so I'm very excited to talk to you about the many types of AI. All of these examples will be in Kotlin, many of them from scratch and not using libraries. So this is all on GitHub. I have all the source code links to these demos. So feel free to explore and check them out. And I'm going to just go ahead and get started because we only have an hour and I have a lot of stuff I want to cover. But feel free to stop and ask me questions if you like. This is very much an interactive session. We'll just see how much we get through. So again, about yours truly, my name is Thomas Nield. I work as a business consultant on an operations research team at Southwest Airlines in network planning. I also wrote 2 books, Getting Started with SQL, as well as Learning RxJava by Pact. I also make a lot of content for O'Reilly Media. I'm actually working on a machine learning from scratch online training for O'Reilly Media, and I'm actually making the code in both Python and Kotlin. So you don't have to take that class. That is on GitHub, so feel free to look in my repository, and you should be able to see all of them there. All right, I'm going to go ahead and skip that just in the interest of time. So I first want to talk about mathematical optimization. And this is something that does not get a lot of attention nowadays because everybody's talking about machine learning, but this is actually very critical. So optimization is a space of algorithms that tries to find a feasible or optimal solution to a constrained problem. So things like scheduling, classrooms, staff, transportation, sports teams, and manufacturing. Finding an optimal route for vehicles to visit multiple destinations. Things like optimizing manufacturing operations, or even solving Sudoku. As a matter of fact, a lot of these algorithms are used in machine learning to minimize the loss and minimize the error and try to find a fit, which I will talk about shortly. But it's a mixed bag of algorithms and techniques, and they can be built from scratch or with the assistance of a library. When you actually take the time to actually try to learn this stuff and you find a few good resources, which I will admit are hard to find sometimes, it's actually it's not difficult to build this from scratch. So the first thing I want to talk about is the traveling salesman problem. Anybody who has seen my stuff on social media knows I like this problem a lot. It is the most elusive and studied computer science problem since the 1950s. The objective is very simple. You have all these points. You need to find the shortest round-trip tour to visit several geographic points or cities. Here's what makes it hard. Just 60 cities will yield 8.3 times 10 to the 81st possible tours. To put in perspective, that is more tour combinations than there are observable atoms in the universe. So very, very hard. So I'm going to go ahead and show, let me go ahead and switch over to my demo slides real quick. Okay, so here is a beautiful map of Europe. And I think there's about 25 cities we need to visit. So if you are approached with this problem of finding the shortest round-trip tour to visit every city, one approach you might reason out, like any good programmer would, is like, okay, well maybe I can start at one random point and then jump to the next closest point, the next closest point, next closest point, and let's just see what happens and see if maybe that will yield a good solution. So it seems to work okay at first until it gets to the end, and then it actually ultimately has to go to those points that are so far away it never wanted to go to them, and therefore you have all of these overlaps in the itinerary. When you have overlaps, this is not good. This means that you definitely do not have a good solution. So one thing you can try to do is you can try to do hill climbing. Start with a random solution, even if it is poor quality, and then repeat the following steps for a number of iterations or until the solution cannot improve anymore. So again, select a random part of the solution and change it. If that results in improvement, keep it. Do this thousands, tens of thousands, hundreds of thousands, maybe even 1,000,000 times, and then ultimately you will converge on a solution. So let's try this with the traveling salesman. I am going to start with a random solution, even if it's terrible, and then I'm going to grab 2 edges at a time, swap them. If that results in improvement, I'm going to keep it. And I do this for thousands and thousands of iterations until finally the solution cannot improve anymore or until I've exhausted all my iterations. Okay, so that looks a lot better. We got 16,718 kilometers as our distance. However, we still can do better than this. So going back to the slides real quick, let me just kind of show what's going on here. So here is a very abstract graph I put together showing all the possible tour configurations and the possible tour distances associated with those configurations. These little valleys right here are called local minimum. And then the lowest one is called the global minimum. So what happens is our hill climbing algorithm keeps making random swaps and finds improvements, keeps those improvements, then finally it gets stuck. And it can't look more than one move ahead to cause an improvement, and so it doesn't see how it can improve anymore because it becomes short-sighted, because again, it can only change one move ahead and it cannot find any more improvements. So we really want to be here at the global minimum to minimize the tour distance. As a matter of fact, we'll even settle for being here, because when you're dealing with more tour combinations than there are observable atoms in the universe, sometimes good is good enough. And so we can actually strive for a better solution and not try to strive for a perfect solution, because perfect is the enemy of good in the real world. So, but how do we escape out of this valley and find a better solution? The key word here is make this algorithm slightly less greedy. Occasionally allow a marginally inferior move to find superior solutions. So what exactly does that mean? So occasionally we allow a marginally inferior move, hoping it will lead to better solutions. So this is simulated annealing, which is a modification to hill climbing that does what I just described. It'll occasionally allow inferior moves, hoping it will find a superior solution. So, but how do you determine whether to keep an inferior move? So there's something called a temperature schedule that throttles periodically between being greedy and random. And if the more random you are, the more inferior moves you'll accept. The more greedy you are, the more you'll only accept improving moves. So a given temperature on a given iteration will result in a weighted coin flip, and that coin flip will determine whether the inferior move is accepted or not. So rather than dive into this equation, let me just open up this Desmos graph real quick, which actually I have open right here already. So here are two variables. This is my degrading distance on a given. So whenever I have an improvement, I always take it. But if I encounter a swap that results in a degradation, it worsens the solution, I'm going to plug it into this function right here. And this D variable, 18,180, that is the inferior move, and this 18,000 is the current configuration. So I'm going from 18,000 to 18,180. Now, don't be overwhelmed by this math function. All it's doing is it's taking those two variables and it's putting it into this function. And this x-axis right here is temperature, and the temperature is just a positive number, and the y-axis is the probability of accepting that inferior move. So if my temperature is really low, like 30, there's only a 0.3% chance I will take that inferior move. But if my temperature is really high, like 120, there's a 22% chance I will take that inferior move. So what I can do is I can kind of throttle between being greedy and being random, back and forth a couple of times, to shake that ball out of the valley and make it go to a lower valley. And notice here as well, the more distance I put between the current configuration and the next configuration, the less likely across the board I'm going to take that inferior solution. So the larger the distance jump is, the less likely I'm going to take it. But the more marginal, the smaller the difference is, the more likely across the board I am to take it. So this clever function allows me to take randomness and steer it a little bit to occasionally allow inferior moves and throttle to being greedy for a certain period of time as well. So let's go ahead and see how this performs. So here's the outline of a simulated annealing algorithm. Start with a random solution, even if it is poor quality. At each given temperature iteration, do the following steps. Select a random variable in the solution and change it. If that results in improvement, keep it. If the result is inferior, flip a weighted coin based on the temperature and degradation, plug it into that function of the move to determine whether to keep it. And if your solution is not acceptable, modify your temperature schedule and try again. So let's try this and see how this goes. So we're going to start with a random solution. And then I'm going to do two random swaps at a time. And occasionally, I'm going to allow an inferior move. And you'll see that little red bar on the left. That is my temperature schedule. So right now it's about 60. And notice that I'm throttling it back up again. So to shake myself out of that valley, that local minimum, I'm going to raise the temperature to make it more random, and then I'm going to bring it back down again, which is what it's doing right now. And notice that it did not settle on the first solution it found. It is still searching and trying to tweak it, hoping to find a better configuration. It's fun to watch, isn't it? Any questions so far? Yeah, it's fun stuff. I think I gave myself carpal tunnel for 2 weeks trying to code this demo, though. It went away, thankfully.
How often do you shake?
That's a good question. So you have to experiment with different temperature schedules, and this is kind of known as the no free lunch theorem. Is just because you found a temperature schedule that works for one traveling salesman problem does not mean it's going to work well with another. And the same applies to machine learning, a lot of non-deterministic algorithms in general. So it looks like it's cooling down, and it is finally arriving on a solution. So notice it's super greedy right now, and it can't take any more inferior moves. And so it settled on 15,349 kilometers, so that's about a 1,000-kilometer improvement. And there's the source code. I also have like a plotter tool where you can plot your own points and see how well it solves it. And that's a really funny XKCD cartoon. So you can actually take this approach I just described to you and apply it to a large amount of problems. So you can do it for linear regression as well. And linear regression, it is literally fitting a line, getting a best fit line through some points. Like if you want to fit a line y equals mx plus b to a bunch of points you just see on the right, you can actually use you can use hill climbing as well as simulated annealing for this purpose as well. Now, but here's the question. M and b are not whole numbers, they're not discrete entities, they are decimals. So how do you determine the random move you're going to do for the m and b values? So what you do is you can use a normal distribution and just randomly sample from it, and essentially the concept of this is you're going to allow some numbers to appear more frequently than others towards the mean, but larger and smaller moves are going to be less frequent. And you can also use a t-distribution which has fatter tails, and it's just a variant of the normal distribution. We'll just keep it at that. And let me go ahead and show that demo. So here is another TornadoFX dashboard I built, and this is all in Kotlin. And I'm going to do that exact same approach that I just described to you. So I'm going to start my line at 0, a slope of 0, and a y-intercept of 0. And then it's going to keep randomly making adjustments until finally it minimizes the sum of least squares. So the sum of least squares, and again, in the interest of time, I'm not going to go deep dive into this too much. It's the difference between the line and the point, and the points y value, and you square that difference, and you're trying to minimize the sum of all of those, and that will give you the best fit. So it's kind of cool. You can completely avoid calculus and gradient descent and all these other more complicated concepts, and instead, I'm just going to randomly adjust values until finally I find a good solution. But you have to control the randomness a little bit and make it go more towards the solution, as well as make it revolve around a mean or a normal distribution. So you can apply it to other variants, quantile regression, which is essentially I want to get 80% of the points under the line, and you can do that too and adapt it easily, rather than spending, 3 days on Wikipedia trying to go through derivatives and other calculus concepts. And you can also fit other nonlinear equations, such as quadratic equations, and other functions. So hill climbing and simulated annealing, they are practical workhorses for a lot of optimization problems, and there are many other metaheuristics algorithms, some of which you might have heard of. So there's genetic algorithms, taboo search, ant-colony optimizations, evolutionary algorithms, as well as k-opt. So Wikipedia surprisingly has a good set of resources on this. You might have heard of genetic algorithms and evolutionary algorithms. And I'm kind of surprised by this because I try to research these. I didn't really play with them very much, but they seem to get a lot of attention now, I guess because they just sound cool, but they don't really work well in practicality. But they do, but they are another form of metaheuristic. And I know the guy at Red Hat who made OptiPlanner, which is basically a metaheuristics library that can do things like solve the traveling salesman problem as well as scheduling problems. He didn't even implement genetic or evolutionary algorithms in the library just because he found the performance just really is not at all on par with hill climbing or simulated annealing and a lot of other metaheuristics algorithms. So we can do a lot of fun stuff with random number generation. And again, it's just going to this concept of rather than having a uniform distribution where any number in a range is equally likely to be selected, you can actually prefer some numbers to appear more frequently than others. And this can be a very powerful tool to do things like create simulations, as well as solving optimization problems like I just showed you. So there's some useful distributions. There's the normal, which I just showed you, t-distribution, which is like normal, but it has fatter tails. There's exponential, Poisson. Poisson's interesting because it shows how the frequency of an event at every time interval. So if I say, hey, on average, I get about 2 customers who walk in every minute, I can plug that into a Poisson distribution and then randomly generate based around that average. And binomial is pretty useful as well. But let me go ahead and show another demo that I have created. Demonstrate this, and again, this is all in Kotlin. So I have 2 distributions that I use to build this. This is a bank queue simulator. And I'm using a normal distribution to randomly generate how long it takes to process a customer. And I'm using a Poisson distribution to show how frequently the customers come in. Okay, good, it's starting, I think. Sweet. All right, here we go. So we have so I'm getting average of 100 customers arriving per hour. I only have 3 cashiers. And the average time it takes to process a customer based on normal distribution is 6 minutes. And so what's kind of cool is if I don't have a lot of data showing how long does it take to process a customer, or how long does a customer wait with X number of tellers, if I don't have a lot of data, I can actually create a simulation to kind of create that data more or less. And then I can wrap an optimization around it and say how many cashiers do I need, and plug it into 1,000 different simulations in order to minimize the customer wait time or make it meet an acceptable threshold. So I can experiment with 5 cashiers, 7 cashiers. You can experiment and modify those parameters in this model if you want to go and download it and clone it off GitHub. As you can see, this is not performing too well. That queue is getting really long. And so I can use this to say, okay, let's try to speed up the processing of a customer or maybe add another teller. And again, simulation's a very fun area to work with. And all you need to know is just a few random number generators. Any questions? Alrighty, I'm going to go ahead and close that. Do a quick cleanup real quick. All right, so let's talk about another problem. This is a problem that, if you were at the talk here last year, I actually did show this problem before. But I probably wasted 50 sheets of paper trying to come up with a solution to this problem. And after coming up with some proofs and not seeing this documented anywhere in books or blogs or any kind of medium, I think I found a solution. It works really well, and you can use this to solve scheduling problems. So you need to generate a schedule for a single classroom with the following classes. I'll talk about how to do multiple classes later. You got Psych 101, which is 1 hour, 2 sessions a week. English 101, 1.5 hours, 2 sessions a week. Math 300, 1.5 hours, twice a week, and so on and so on. So you have all of these classes. They each have a set number of recurrences. They each have a different duration. And you need to schedule them from Monday through Friday, 8 a.m. to 11:30 a.m. and 1 p.m. to 5 p.m. And the slots are scheduled in 15-minute increments. All right, so this is terrible. This is like a really, really hard problem to deal with, and it actually is very hard. And it's kind of funny is when you're dealing with optimization problems, you're dealing with something as mundane as trying to schedule staff or trying to schedule classrooms and dealing with union restrictions, vacation requests, trying to minimize the cost of your employee wages or make them meet an acceptable threshold, trying to manage their seniorities and give them preference. When you're dealing with all these constraints, it can get very difficult, very gnarly, very quickly. And so it's interesting. You can take mundane problems before you know it, you're dealing with astronomical numbers of permutations and how to solve it. So you can actually use the hill climbing and simulated annealing to solve a problem like this. Something like this, though, there's another approach. You can do a tree search. So first, visualize a grid of each 15-minute increment from Monday through Saturday or Sunday, intersected with each possible class. So each cell will be a 1 or a 0, indicating whether it's the start of the first class. I'll talk about how to solve for those 1s and 0s shortly. But again, there's just that occupied state shared between a given slot and that class. Next, visualize how the overlaps will occur. So notice how a 9 a.m. Psych 101 class will clash with a 9:15 a.m. Sociology 101. So look at that 9:45 a.m. slot and see how when Psych 101 is scheduled at 9 a.m., Sociology 1 is scheduled at 9:15 a.m., that causes the 9:45 a.m. to be double booked. And the way you can look at this is all the slots that touch that 9:45 a.m. block, they must sum to no more than 1. So if we push it out to that sociology to 9:30, there's still a conflict, the sum is still 2. Push it to 9:45, there's still a double booking, the sum is 2. But as soon as the sum is no more than 1, we're good to go. That constraint has been met. So for every block, we must sum all affecting slots shaded below, and you can identify these purely from the class duration. So that's Psych 101, it's a 1-hour class, therefore the 4 slots preceding and before that 9:45 a.m. All of these blue shaded regions on that 9:45 a.m. based on the class durations must sum to no more than 1, and that is how you model the constraints. And again, I'll talk about how to solve for the 1s and 0s next, the start of the first class. Taking this concept further, we can also account for the recurrences. And not just do the duration, but actually account for the recurrences too. So the 9:45 a.m. Friday slot, that, if linear algebra is scheduled at 8 a.m. on Monday, that will also cause the 9:45 a.m. on Friday to be occupied. So a lot of the work in creating these constraints is actually trying to query out all of these slots that affect a given block of time. And then when you plug this into an optimizer, you build the tree search algorithm from scratch, it's actually relatively easy to do. Computationally, it's a little expensive, but it's not hard to model once you have the model down. Well, once you have the model down, it can be much easier to solve. And so plug these so you can use a library like OJ-Algo or OptiPlanner to solve for a solution and plug these constraints into it. I'll kind of walk through how you can do it from scratch as well. If you're comfortable with recursion, that's half the battle. So this is the solution you'll see on the right, but let me talk about how you can solve for the 1s and 0s yourself. So hold that thought, let's talk about state space search. Imagine you were presented a Sudoku. Rather than do an exhaustive brute force search, think in terms of constraint programming to reduce the search space. So first, sort the cells by the count of possible values they have left. So if you look at, hopefully Sudoku is familiar, every row, every column, every square of 9 cells must have the numbers 1 through 9. And so if you look at a given cell, like the center one, let me go ahead and show the next slide. So cell 4-4, that very center cell, can only be a value of 5 because that is the only number that's not in that row, in that column, or that square. So we sort the cells sorted by the possible candidate count. So cell 4-4 can only be 5, 7 can only be 3, then 1-4 can be 2 or 5. Finally, at the very bottom, 2-6 has the most possible values, 1, 3, 4, 5, 7, 9. So take those cells, sort them by the number of candidates they have, and then with this sorted list, create a decision tree that explores each Sudoku cell and its possible values. So this state space search technique is called branch and prune. So you can see here we start at 4-4, it can only be 5, so we move on to 7-7, which can only be 3, 8-6 can only be 4, but notice when we get to the 1-4, we now have 2 directions we can take. We can explore the 1-4 being a 2. We can also explore it being a 5. So we'll go down the 2 first, assuming we do depth first. Then 0-7 can only be a 3. Cell 3-2 can only we're going to explore 0-7 being a 3. We're going to explore 3-2 being a 3, and then cell 4-2. We'll explore that being 3, but then we're going to stop right there because we already have. It's not apparent because this is not on the grid, but we already have a 3 in column 2. So we stop that branch right there, stop the recursion, and then we move on to the next available branch, which is exploring 4-2 being a 4, and so on. So we keep doing this recursive search. We try to prune it and constrain it. What's up? Oh. That's okay. It's the motion sensors. Okay, that took me a while. I'm sorry. So anyway, so you just keep doing this recursive search until finally you solve for all 81 cells. And as soon as you have a branch that provides all 81 cells and that last cell did not break any constraints, you have solved your Sudoku. Then you can collapse that branch back into the Sudoku board. And so I actually have this coded. So I have 2 implementations for my Sudoku solver. I have my own branch and bound built from scratch in Kotlin. I also have OJ-Algo, which models it as an integer linear problem. So I'm going to use my branch and bound. This is I punched in these values. So when I solve this, it should solve pretty quickly. I think I plugged in so there is the world. I saw this article that was talking about the world's hardest Sudoku. It's a couple of years old. I plugged it into this and using my branch and bound algorithm. It took about 3 minutes to solve. So it's interesting to watch the values flip around and everything, and as it struggles to try to find a solution, but it solved the world's hardest Sudoku in 2 or 3 minutes, so I will take that. So, and this kind of goes into the PNP territory, and I like using the Sudoku as an example because some problems solve extremely quickly while others take a really, really long time. And this is what makes this problem space so difficult and so fun, is that you can't just predict how long it's going to take. And you have to use heuristics, which are clever search strategies like the ones I showed you, to kind of guide it towards the most likely solution first. In this case, the heuristic was sorting the cells by the number of candidates they have and start with the most constrained cells first, because that narrows our search space drastically. So going back to the scheduling problem. You can solve the scheduling problem from scratch with branch and prune. Start with the most constrained slots first to narrow your search space, like the slots fixed to 0 first, followed by Monday slots for 3 recurrence classes. So if you have a class that's 3 recurrences, and assuming there's a day gap between each recurrence, there's no reason you should explore that being Tuesday, Wednesday, Thursday, Friday. Those have to be on Monday, so you search for the 3 recurrence classes to be scheduled on Mondays first. And then just completely get rid of the other slots that are infeasible already that you know, or just put them at the very bottom so it never even gets there. And so this is what makes optimization fun, is you have this game of trying to think, how do I make my algorithm go towards the most likely solution first and do it quickly? And hence, practically prune the tree as you go, eliminating any slots ahead that must be 0 due to a 1 decision propagating an occupied state. So that tree, if you've already scheduled Biology 101, you should not have to explore Biology 101 being any other time going forward in that tree. If you want to schedule against multiple rooms, just plot each variable using 3 dimensions. So we're just doing 2 dimensions, but if you want to do a third one for different rooms, pretty much the same concept, except you're now tying the occupied state to a specific room, and you make sure the rooms are not double booked, just like the slots are not double booked. So I ran this earlier before we got started. So here is my algo. So here is this is the one I wrote. This is actually using OJ Algo, this one I ran. So OJ Algo, when I ran the scheduling problem on it and it solved for the 1s and 0s, I also have another implementation in the source code that uses my own from scratch algorithm. This is the schedule it outputted. So you can see if you take those classes and plot them, you'll find that there's no overlap and all of our constraints are met. Any questions?
Are you actually getting to use these like day to day?
Yes, I actually do. I actually am working on a very huge project like this that does optimization, and that is something I do in my daily work. I can't talk too much about it, but yes. And the thing is, when you think about like airlines and a lot of industry in general that are dealing with the very hard concrete problems that are very physical, this is very much what is dealt with on a day-to-day basis. I mean, especially when you're dealing with physical, where you can't have something occupied twice, and that happens everywhere. Any other questions?
Can you keep adding more dimensions to this as well?
Yep. Yeah, it'll be very difficult to visualize, but yeah, you can do 4, 5, 10, 20. As a matter of fact, you can have 1,000 different dimensions, and you can buy commercial solvers from like IBM. They have Cplex and stuff if you don't want to do that yourself and have them do it more efficiently. So yes, you can do as many variables as you want. Of course, it might get harder and harder as you do. And that's, yeah, I was just showing a problem that only had 2 or 3 dimensions. And in the real world, you may have like 20, 30, 100. Those are some great resources if you're interested in optimization. I highly recommend checking them out. And that Coursera class is very difficult. It will challenge your programming skills, but it is amazing. It talks about a lot of the stuff I just talked about right now. Okay, let's see where we're at. I think we're actually doing pretty good on time. Awesome. Okay, so I only have 2 more. I think I only have 2 examples left. Let's go ahead and keep going. Let's talk about machine learning. So probably the most common task in machine learning is classifying data. How do I identify images of dogs versus cats? What words are being said in a piece of audio? Is this email spam or not spam? Or if you've ever watched Silicon Valley on HBO, hot dog, not hot dog. What attributes define high risk, medium risk, and low risk loan applicants? And how do I predict if a shipment will be late or earlier on time? So there are many techniques to classify data with pros and cons depending on the task. So there's neural networks, which has been popular for quite a couple of years. Support vector machines, decision trees, random forest. I hope to do a talk on this example I created recently in the future, but unfortunately I don't have time today. As naive Bayes, as well as linear and different regression models. So let's focus on naive Bayes because it is simple to implement and effective for a common task, which is text categorization. So naive Bayes is an adaptation of Bayes' theorem that can predict a category C for an item T with multiple features F. And so a common usage example of naive Bayes is email spam, where each word is a feature, and spam or not spam are the possible categories. So let me go ahead and do a quick demo just to kind of show why this algorithm can be pretty cool. Okay, so I have here this dashboard I built. And I have some bank transactions I'm going to input, and I'm going to slap a category on each one. I'm only going to look at the memo field to figure out what the category is. You can also use logistic regression for this, but naive Bayes is the most common implementation used, so I'm just going to focus on that today. And how you can build it from scratch, because it's actually not hard to do. So I'm going to input this first transaction. I'm going to clipboard it. Now notice it did not give it a category yet because it has no data at all right now, so I'm going to categorize that as grocery. And then here's a coffee shop visit. I'm going to add that. And then I'm going to categorize that as coffee. So again, it's not making any predictions on what the category is yet because it doesn't have very much data. And then here's an Amazon purchase. Again, doesn't know what it is, so I'm going to categorize that as electronics. Now this is where things start to get interesting. Here is an Amazon video on demand. So this was a movie rental. And it's going to categorize as electronics because it got triggered by the Amazon keyword. It's like, oh, that's electronics. So I'm going to say, no, this is entertainment. Now what's interesting though is even though I've kind of thrown an ambiguity at it, it will use the combinations of words and the probabilities of those words, in aggregate to figure out what category it belongs to. Now I'm going to pull in Starbucks coffee. And it categorizes as coffee. And I never gave it a Starbucks transaction before, but it did see a coffee shop transaction that looks similar, so it's like, okay, I'm going to categorize this as coffee. And it's probably triggered by the coffee keyword. And then let's do Redbox video rental, which again, I've never inputted a transaction for before. And it's going to categorize as entertainment. So the more data I give it, the smarter it gets. And what it is doing essentially is it is using and I promise I am not using any word bags or lookups or anything or indexing the words. It is just dynamically combining the probabilities of each word occurring in a category versus not occurring in that category. And if I give it more examples, let's see if this one actually works or not. So if I do a car rental, it can categorize that as entertainment, but that's going to categorize that as travel. And then at that point forward, it's going to start making that delineation. It's like, okay, well, rental could be in travel. It could also be in entertainment. I'll use the other words to kind of infer the rest. So how exactly do you implement this? And it's actually not terribly difficult. So naive Bayes, it's an adaptation of Bayes' theorem that can predict a category C for an item T with multiple features F. I'm speaking in Java or Kotlin generics right now. And a common usage example of naive, I already did this slide, sorry. So naive Bayes works by mapping probabilities of each individual feature occurring or not occurring for a given category, such as a word occurring in spam or not spam. So a category can be predicted for a new set of features by 1 for a given category. Combine the probabilities of each feature occurring and not occurring by multiplying them together. So you got the occur product, you got the not occur product, and you multiply the probabilities of each word occurring in that category just by summing the words and then dividing by the count of all the words. And then divide the products to get the probability for that category. So take the occur product, divide it by the occur product plus the not occur product, and that will give you the probability that set of words belongs to a given category. So calculate this for every category and just select the one with the highest probability. There's your naive Bayes algorithm. Now there is one caveat you got to deal with. Computers do not do a great job of keeping track of decimals. And so to deal with floating point underflow, here is a clever math hack you can do to work around that. So when you're multiplying a lot of small decimals, which can happen with probabilities, that can cause a floating point underflow where it gets so small the computer can no longer keep track of it. So to remedy this, transform each probability with a log function or a natural log function and sum them. And a logarithm, I'm not going to go into too much detail. If it's not familiar, all it's essentially doing is we're exploiting a property it has where we can bypass the multiplication by doing addition instead. And so we'll convert each of those values using a logarithm, and that will allow us to do the multiplication by adding the values instead. Then we can call the exponent function in Kotlin standard library to convert the result back. So there is our new occur product, not occur product. We just take the natural log of each one, and then we wrap that up in an exponent to convert the result back. So that allows us to avoid multiplication and instead do addition instead. And one last consideration, never let a feature have a 0 probability for any category. Always leave a little possibility it could belong to any category so you don't have 0 multiplication or division mess anything up. So just add a little bit of a small number to the numerator and denominator, like it can be 0.5 or 1.0, so that way you never have 0 division mess anything up or a 0 probability mess anything up. It just cause the entire thing to go to 0. So machine learning, this happens a lot, fudging the numbers just a little bit, because machine learning is not really deterministic and it's an estimate in the first place. And so this is a little hack you can do to avoid problems with 0. So if you want to learn more about Bayes, those are some 3 great resources. And those are the source code. I also have an email spam classifier example. Any questions before we go to the final part on neural networks? Well,
instead of doing 0.3 times 3, sorry.
Yeah. So yeah, right. So when you multiply a lot of decimals together, it could go into a floating point underflow. And so a little mathematical hack you can do to work around that is you use a log function on each of those numbers, and then because logarithms have an additive property, you can just add those numbers instead and effectively do the multiplication that way. And then you call exponent on the result to undo the logarithm and convert the result back. So yeah, I should have explained that a little bit more clearly. I'm sorry. But yeah, so and I've seen that used in multiple places. Like it's helpful to use in like logistic regression and everything, and a lot of machine learning algorithms as well to kind of bypass the whole the decimal underflow. Anything else? Alrighty, let's talk about neural networks. Okay, so neural networks are a machine learning tool that takes numeric inputs and predicts numeric outputs, pretty much like any machine learning algorithm. And then a series of multiplication, addition, and nonlinear functions are applied to numeric inputs. And then you keep iteratively tweaking those mathematical operations above until the desired output is met. So here's a very simple problem I like to use. Suppose we wanted to take a background color in RGB values, red, green, blue values, and predict a light or dark font for it. So if you search around Stack Overflow, there is a nice formula to do this for you already. And that is that formula right there. And I believe if it's greater than 0.5, it's going to suggest a light font. If it's less than 0.5, it'll suggest a dark font. I might have flipped that, so don't hold me to that. So, but what if we do not know the formula or one hasn't been discovered? Ideally, we use machine learning to surface models we know nothing about. In practicality, especially with neural networks, it's one big black box to the point. The creators don't even know what's going on inside. They say, okay, it's working. Or no, it's not working. Let me see if I can do something to correct it. It's highly experimental and it's sometimes kind of unpredictable. So let's represent background color as 3 numeric RGB inputs, and we're going to predict a dark or light font that should be used. There's this mystery math in the middle, which I'll get to shortly. I have those 3 RGB values being inputted, and it's going to spit out 2 numeric values, two numeric values between 0 and 1. And the top one is going to recommend light font. The bottom one is going to recommend dark font. So the one that's the highest is the one that wins. So when you use machine learning libraries, this is kind of the process. You have this library, you give it inputs, there's this mystery math inside the library, then it outputs the result. So this is the mystery math right here. And it actually is, this may look like a lot, but it's actually pretty straightforward. It's really just doing some multiplication and addition. You have this middle layer that will take each RGB input value, multiply it by respective weight, tied between that input node and that middle node, and then I'm just going to sum them, and that will result in a number. And then on that final layer, which spits out the light font or dark font recommendation between 0 and 1, it's going to multiply and sum again. So in linear algebra, this is called a dot product, but really it's just doing multiplication and addition. And you have those weights established between each node, between the first layer, the second layer, and the third layer, and you multiply each of the incoming input values by that weight, and then you sum them. And then and you do the same thing with the last layer again.
Try to find the cases where it would predict 50%.
Yes, that does happen. And usually I think like the cutoff, typically if it's 0.50, you just round up.
What do humans think about these cases? Do you look at the colors reading and what they
Sorry, repeat that one more time.
If you have a 50% chance of each, did you look at the colors to see if humans would prefer one or the other?
Well, each of those, so the way this is set up, those two values are kind of siloed from each other, so it's unlikely you're going to get 50-50, it's because, again, those are kind of siloed from each other. Now, you probably could configure it in a way where it does enforce that.
So you have no control. You don't put a control on your values. They can explode and get above.
They can, and I'm going to get to the next part next. But this is architecturally how it works. But this is the next part. So each weight value, I'm sorry, I should have gone to this earlier, should be between -1 and 1. Now, this is the million-dollar question. What are the optimal weight values to get the desired output? So the answer is, this is an optimization problem. And this is something I wish a lot more people would talk about with machine learning. They just completely gloss over the optimization part, but that's really the heart of machine learning, is it is actually an optimization problem. That's why machine learning is expensive. That's why it takes so long to compute, because it is trying to search for those weight values that optimize the neural network and make it as close to the training inputs as possible. So as you can see here, it's not going to be strictly 1 or 0 on those output nodes, but the highest one is the one that's going to win. So we need to solve for the weight values that gets our training colors as close to the desired outputs as possible. So just like the traveling salesman problem, everything comes full circle. You need to explore configurations seeking an acceptable local minimum. So the most conventional way to do this is using a technique called stochastic gradient descent, which is similar to hill climbing, but it uses calculus and a derivative to steer the direction. But you can actually use hill climbing and simulated annealing to solve for those weight values as well. And I actually have multiple versions of this solver built that uses those different approaches. So, and as a matter of fact, using simulated annealing, I've not done this myself, but I've read some academic papers. You can actually get better performance out of simulated annealing than stochastic gradient descent, although it does have a little bit more of a computational cost. So, I'm going to switch over to the final demo. So I have different machine learning implementations for this problem, including decision trees, random forests, linear regressions, logistic regressions. Unfortunately, I don't have time to talk about all of them today. I'll save that for next time. So we'll talk about the deep learning part for now. And even then, I have different implementations. So I have a hill climbing version I built from scratch. I have a simulated annealing version I built from scratch. And there's also these two using libraries, OJ-Algo as well as Deep Learning 4J. Deep Learning 4J is basically Java's TensorFlow. So I'm going to go ahead and just use OJ-Algos. And I've set up this model right here to accept inputs to train. And it's going to say, okay, which looks better? And I'm going to say, okay, light looks better, dark looks better, dark looks better, light looks better, dark looks better, light looks better. So I can start training my algorithm and start giving it inputs and putting labels on them. And then my hope is when I predict a color, it will start getting accurate. But the thing is, I only gave it like, 7 or 8 inputs, and it's predicting a dark font for black. So this is the thing about neural networks. They are extremely data hungry. You have to give it a ton of labeled data, and that data often manually has to be labeled for it to become effective. And even then, you can run into overfitting problems where it only works with the data you're trained with, but then there's new data it hasn't seen before, and then it starts acting completely wrong again. So what I'm going to do here is I'm going to save some time. I'm going to train it I'm going to give it a training set of 1,345 colors that are pre-labeled and ready to go. I really cheated. I just used that Stack Overflow formula to apply the label. So I ran that, I trained it, and now look at that. It actually does a pretty good job now. So it's predicting a light font for black, so that's good. And when I give it white, it predicts dark. So again, neural networks, they're very data hungry. You have to give it a lot of labeled data. And but once you have that, and you don't veer too far away from your training data set, then you should have an effective model. Now again, this is probably not the best machine learning algorithm to use. Like, you can use decision trees. Logistic regression would probably work pretty well for this as well and be less expensive. But that is neural networks in a nutshell. Oh, also one thing I forgot to mention, activation functions. So you might want to consider using activation functions on each layer. So after you take that sum value, you're going to use a nonlinear function like ReLU or softmax to smooth the value and actually make that layer do something productive and compress that value. And these are 4 common activation functions implemented from scratch in Kotlin. So there's sigmoid, which compresses the value between 0 and 1, resembling a probability. ReLU, which zeroes out all negative values. TANH will compress the values between -1 and 1. Softmax is interesting. What softmax will do is it'll take the highest value and push it up even more and then dampen the other values so that it's pretty helpful for classification. So it makes that one classification stand out even more, and this helps with the training. And again, you don't have to use gradient descent to solve it. You can use other optimization algorithms, including the ones I showed you with the traveling salesman. So there's other architectural decisions, like how many middle layers do you need, how many nodes should you use, what activation function should be applied to each layer, and the loss function, how should we measure error. So you can just use the sum of least squares, the average of the squares, to say this is what was predicted, this is what the actual was. You know, take the difference and square it, and that is how off it is, and you sum those or average them and try to minimize that. And I want to throw in just some of my personal thoughts as well, the practicality of neural networks. Like I said, they require lots of labeled data. They are great with image recognition and audio recognition and certain other spaces of task, but they do have a diminishing return for problem spaces outside of image and natural language processing. And it's interesting, people have tried to solve it. There are academic papers trying to solve the traveling salesman problem with a neural network. And while it is interesting, you can structure a problem that way, the results are pretty underwhelming and it's not necessarily effective. And not to mention, it's kind of circuitous too, because it's like, wait, I'm using something that could be solved with an optimization problem is instead using machine learning, which uses optimization. So it's a much more convoluted architecture. And so why not just go straight to the optimization part, which is what's driving the machine learning in the first place. And so in reality, specialized and incumbent algorithms will outperform neural networks for most practical problems. And these are some 3 great resources if you want to learn more about deep learning and neural networks. I also have a blog article, shameless plug, talking about the fact that we've been in AI winter 2 or 3 times since the 1950s. And I personally believe, and there are other people who believe much smarter than me, that we are headed towards another one very quickly. Because when you have that bubble of people putting all this faith in AI, thinking that we're reaching singularity and we're reaching Skynet-like levels, we are nowhere near that, so don't believe the media, no matter what they tell you. Skynet's not coming. And all the source code is here as well if you want to look at it. And so, so just to summarize this, I just want to emphasize, use the right AI for the job. So neural networks, like I said, they work great for certain problem spaces, especially for fuzzy problems like picture and audio and video recognition. If you have a lot of labeled data, that's great. Bayesian inference works great for like email spam, sentiment analysis. So you can use naive Bayes to categorize tweets and say these politicians, how much of these tweets are positive, or many of these tweets are negative, or you can make it more specific. How many are happy, frustrated, sad, etc. And you can use that to apply different classifications. And then also, if you're trying to solve things like transportation, industrial problems, scheduling server jobs even that you don't know how long will take, or they take some amount of time and you want to plan and pack them together, optimization works great in that space too. So that is it. That is my presentation. Please the slides are available on the meetup for this page. There's also some appendix which has some other resources, some fun links, etc. on my classes, and just things that I think people would find useful. So thank you very much.